pulling in half.
Yes, thank you for the introduction. Also, thank you for inviting me to speak. So I should maybe start with saying that if I say something you're not familiar with, especially the geometric stuff I just heard, please interrupt and ask, because this will be a bit of a geometry-heavy talk maybe for a topology seminar, but we'll see. And I should also say that this is all joint work with Alfredo Pino, who's also based in Utrecht, and Laurent Toussaint, who's currently based in Amsterdam at the VU. So, yeah, I want to tell you today about wrinkling and half-flicker structures, but let's start very generally. So, what are we actually interested in today? So we're interested in studying the topology of the space of geometric structures on a manifold M. And here I'll loosely define a geometric structure as some section of a fiber bundle psi satisfying some condition on its derivatives. So keeping the study of PDEs in mind, you could say it's a solution to a partial differential relation, where a relation really generalizes a PDE because we'll allow for inequalities, for instance. And as such, I will also not say from now on really that we're studying geometric structures, but I'll say that we're studying solutions, and the space of geometric structures I'll hence denote by this sol R. And then some examples. So for a geometric structure, you could keep in mind contact structures, symplectic structures, but also immersions, submersions, foliations. Really, a lot of the things you would study in differential geometry fit this setup. And then there are many ways you can, of course, study this space of solutions. And one way would be from an H-principle perspective. And then the strategy is to not study the space of solutions directly, but instead introduce a larger space of formal solutions, which is usually easier to study because it's of a more algebraic nature. And then you study this space of formal solutions, and the inclusion of solutions into formal solutions. And then in the best case, at least from a topological perspective, this inclusion is weak homotopy equivalence, meaning, and then we say that the differential relation satisfies the H-principle, which is then short for either homotopy principle or weak homotopy equivalence principle. And then what are these formal solutions? Well, you could think of them as almost solutions. They're not really what we're interested in, but they're close in some sense. And for that, we need to define jet bundles. So given the original fiber bundle psi, we can construct its rth order jet bundle, and that's a bundle consisting of Taylor polynomials of order R of sections of the original bundle psi. So it is a fiber bundle in itself. And if you have a section of the original bundle psi, you can take its jet, meaning that you take its Taylor polynomial on each point, and that gives you a section of the jet bundle. So I've depicted it here at the bottom. So in dark blue, we have the actual section of psi. And then in 3 points, I've also indicated the jet, meaning that I've also included its first order data, which is just the slope of the section. And in this setup, a differential relation is then a subset R of the jet bundle. So those are all the Taylor polynomials we allow for. And then formal solutions are sections of the jet bundle with image in R. And then solutions, so the things we're actually interested in, are sections of the original bundle psi, such that their jet has image in R. Differently put, you could say that a solution is a section of psi such that its jet is a formal solution. Now, as an example, we could study submersion, so the submersion relation. And officially, usually we say that this is a relation between maps, so you could do this all setup for maps between manifolds. You could also say that the map from M to N is just a section of the bundle M times N over M. It boils down to the same thing. But then in this case, a formal solution or a formal submersion is just an epimorphism between the tangent bundles. So capital F here is of maximal rank. And then an actual solution, so an actual submersion, is a formal solution where capital F is actually the derivative of lowercase f, so the map it lifts. So here you see that formal solutions are a sort of decoupled version of solutions, and they correspond to an actual solution if they integrate to a genuine solution, or the solution of the bundle psi. Now then, a central question when you're studying H principles is, if I have a formal solution, can I deform it or can I homotope it to an actual solution? What we mean by that is whether we can deform a formal section into a holonomic section, which are exactly those sections which integrate to a section of the original bundle psi, meaning that they're just the jet of some section. Because those holonomic sections, which are also a solution, which are also a formal solution, are the genuine solutions we're interested in. And then in practice, we're interested in the slightly stronger question. So if I have a formal solution, can I approximate it by a holonomic section? Because then you can just use a linear interpolation to find your homotopy. However, as the slide already reveals, you cannot always approximate a formal section by a holonomic section. That's depicted at the bottom. So in this case, we're studying maps from and to the unit interval. And the formal section has a zeroth order data being the identity, and its first order data is having zero slope. Well, this is not a holonomic section itself, because if you're a map between the unit intervals and your zeroth order data is being the identity, then you have slope 1 and not slope 0. So this section is not holonomic. But then you may wonder, can I approximate it? Well, if you're approximately the identity map, you will always also have approximately slope 1, which is not approximately 0. So this formal section cannot be approximated by holonomic section. But there is this theorem by Gromov, Eliashberg, and Michachev, which tells us that under some conditions, holonomic approximation is possible. But there are some drawbacks. So for instance, we cannot do holonomic approximation over the entirety of the manifold. Instead, we can only achieve, at least in the setting of this theorem, a holonomic approximation over a subcomplex of the manifold of positive codimension. And in fact, we also need to allow ourselves to wiggle this subcomplex. So we need to allow ourselves to perturb this subcomplex, and then over this perturbed version, we can do holonomic approximation. So I've included a picture, which hopefully clarifies it a bit. So I've drawn again the same formal solution, but now I've extended its domain. So I've added the -1 interval, and I've extended the formal section by just making it constant over that extra direction. And then what the proof does is actually something what you may do in real life. So imagine you're standing in front of a mountain and you want to go to the top with preferably a 0 slope approximately. Then you do not just go up in a straight line to the top of the mountain. Instead, you take a lot of turns so that you have a slope of whatever you like, epsilon. And that is also what this greenish holonomic section does. So it takes a lot of turns, but it does have slope epsilon, and hence it approximates the formal section, but not over this unit interval A, but instead over a wiggled version. Yeah, I hope that's somewhat clear, but the main takeaway is that if you allow some flexibility, holonomic approximation is possible. And this is in fact the main ingredient of this theorem by Gromov, which states that if M is an open manifold, that any open and diff-invariant differential relation R satisfies the H principle. So if you're being optimistic, you could say that this theorem shows that half of the H principles hold true, because the open manifold case is solved and the closed manifold case remains, because the open and diff invariance is not that strong of a condition. So I should now tell you what those conditions are. So open just means that the relation is open as a subset of jet space. So this encodes some sort of stability, because if you have a solution, be it formal, be it a genuine solution, you can perturb it a little bit and then it will remain a solution. Diff invariance is slightly more technical, but it means that if you have a solution, you can pull it back by a diffeomorphism, and that result should again be a solution. And then again, this should also hold for local solutions and local formal solutions. And in practice, this just boils down to the fact that you should be able to define your relation in a chart-independent way. So that's also usually fine. Yeah, but, oh yeah, first I want to do the corollary. So I listed some examples at the beginning of geometric structures, and this theorem then has as a corollary that contact structures satisfy the H principle in open manifolds. The same for immersions and submersions, because they're open and diff-invariant relations. The symplectic relation is diff-invariant but not open, but you can do a small trick, and then also this theorem applies. So also for symplectic structures, the H principle applies. However, the openness of the manifold is really important here, because the H principle is just false for contact and symplectic structures and for submersions of closed manifolds. Exactly because this theorem uses holonomic approximation, meaning that you need some source of flexibility to wiggle your manifold. But on closed manifolds, you do not have this, because in some sense, you do not have an infinity towards you can push your problems. So on closed manifolds, we need a different source of flexibility to be able to homotope our formal solutions into actual solutions. And one option is to allow for singularities. So that's the approach we'll take today. So now I first want to introduce you to a specific type of singularity and argue that it's quite a mild singularity, because we do not just want to allow for any singularities. So let's again consider the submersion relation. Then a singularity just means that the map is not a submersion there. So a map is singular in a point X if its rank is not maximal there. And then the claim is, I'll wave my hands here a little bit, that the easiest singular map is the wrinkle, and in fact, it exists for all combinations of dimensions. So it is actually a family of singular maps. Now, I don't want to show you the equation, because I don't think that's very useful. Instead, I've drawn the graph of the 1-1 wrinkle, which is just a map from R to R. It looks like what you see on the left. I've also drawn the image of the 2-2 wrinkle going from R2 to R2. Maybe that needs a little bit more of an explanation. So you could interpret it as a family of singular of maps. So it's first regular, and then a wrinkle is born, a wrinkle like on the left side. The wrinkle gets larger and becomes smaller, dies off again until you have regular maps again. So in this middle part, you have 3 layers of R2, so to say. And this is also how it gets the name, because this is exactly a wrinkle in your clothes. Now, there are multiple arguments for this claim, why it's a mild family of singularities. One would be, for instance, that its singularities are contained in a compact, which is always nice. You could also do some singularity theory and classify the singularities, then you'll see they're not that bad. Another reason is more applicable to H principles, and that states that a wrinkle formally regularizes, meaning that if you have the wrinkle, you can take its jet, and that jet will not lie in the submersion relation because of the singularities. However, you can homotope this jet as a formal section, such that it does have image in the submersion relation. And that result is referred to as the regularization of the one jet of the wrinkle. So yeah, that is a formal submersion, and yeah, it's uniquely defined up to homotopy. How does this look like? Well, I've depicted it here for the 1-1 wrinkle. So on the left, you see its jet. I've now indicated its first order data by these arrows. And then you see the two problematic points where the derivative is 0, so where it's not a submersion. And what we just do is that we homotope it as a formal section, so we just homotope its first order data. We do not change its 0th order data, and we just increase the, so to say, derivative. And then we get something like on the right, where the derivative is always, well, derivative, so to say, is always positive, meaning that it is a formal submersion. However, it's not a holonomic section anymore. It does not correspond to an actual map between manifolds anymore. Okay, and using these types of mild singularities, Iliasberg and Mitsachev prove a sort of holonomic approximation theorem, but then in the specific case of submersions. And specifically, this theorem also holds for closed manifolds. So that's why we need to use singularities here. And it states that if you are given an epimorphism, meaning a formal submersion, then there exists a wrinkled submersion, which is just a submersion whose singularities locally look like one of those wrinkles on the previous slide. And this wrinkled submersion is close to the map underlying the epimorphism we're given. And if we take the jet of this wrinkled submersion and regularize it, the result is homotopic to the given epimorphism. So this is in some sense the best we can do for submersions over closed manifolds in an H principle direction. And our goal was now to generalize this theorem for to hold not just for submersions, but for this class of open and diff invariant relations for which also the H principle of open manifolds holds. And for that, we need to extend this jet tower we saw a bit. So, okay, officially I just introduced one jet bundle, but you can of course stack them on top of each other, and then you get a tower of jet bundles. And then you have these maps going downwards, and the index indicates their target. So by the P0 goes to the 0th order jet bundle of psi, which is just by psi itself, and I use B for projection onto the base. Now, well, then you can stack all of these jets, and at the very top you find germs. So germ space consists of germs of sections of psi. And then, of course, you have the same maps going down. And now we also have this PR going to the rth order jet bundle. And whereas the rth order jet bundle had quite a natural topology, this is slightly less natural for germs. So what we do for the rth order jet bundle is that in each point you take a Taylor polynomial. So you can also just take the Taylor coordinates, and those give you charts. So that's quite a natural chart. For germs, you cannot do that. If you would try to do something, you would end up with an infinite dimensional space. So what we do instead is that we use the projection onto the base, so PB, to endow germ space with the étale topology, meaning that we just require that projection onto the base is a local diffeomorphism. So germ space, I'll also refer to it as étale space because of this reason, consists of a lot of like horizontal sheets of M that are all glued to one another in some possibly very difficult ways. And then with this germ space, we can generalize this theorem about wrinkled submersions. So we are now given a section of the jet bundle. And then we say that there exists a wrinkled submersion G to germ space, such that if we project it down to the rth order jet bundle, that this is a approximation of F. However, in general, it will not be a section. I have a picture of G in a minute, so there you'll see it, that it is indeed not a section. But not all is lost because the next two items tell us that it is in some sense close to being a section. Because if you have a section and you project down to the base, you of course get the identity map. Now with G, that's not the case because it's not a section, but instead you get a map if we project G down to the base that is close to the identity. And in fact, it is a wrinkled submersion, meaning that we can, again, consider it's one jet, and in fact, it's regularized one jet, and this will be homotopic to the given section F. And now you may wonder, why would you still call this a holonomic approximation? And that's exactly because we're mapping into germ space, so locally we're selecting just germs of a section. So locally you could say G is the image of one section. So it is graphical over the base, over a dense subset, for instance. You could say things like that.
Quick question. So here you don't
Yes.
fix any differential relation.
No.
General differential relation. But if you do,
Yes.
could you say the homotopy of the jets go via the
Yeah, if your relation is open, then again you can use the linear interpolation to obtain a homotopy via formal solutions. Yeah. More questions? Okay, then we'll do a proof by picture. So the idea of the proof is basically the following. So what we do is we take a sample of a formal section. I've now taken a sample consisting of 3 points. And then we find some holonomic extensions, meaning that we find some jets of the original bundle psi, such that, for instance, in X1, its jet agrees with F in X1. And now the observation is that if you would just interpolate in between F in the sample points, you would have quite a large slope. Whereas we want again to have a zero slope because that's what F is. However, we get a smaller slope if we interpolate from the beginning of one sheet to the end of the next sheet. So that's exactly what we're gonna do. So G, or at least its projection down to jet space, will look like this. So what do we do starting at the left? Well, we interpolate to the end of, well, in this case, the first sheet. Then we use a wrinkle to turn back to the beginning of that first sheet. Then we interpolate to the end of the second sheet, use a wrinkle again to go back, and we continue in this fashion. So you see, it's not a section. You could call this a multi-section. And because if we construct it in this way, it actually lifts to étale space, because in each sheet, we can just take the germs of the section. So here you already see a bit what you would call it holonomic approximation. And then also the interpolation you can lift to a tile space. And yeah, that's basically the proof. And on this level, I must say, it's really similar to the proof of the wrinkled submersion. This is really a generalization of that proof. And you could say, in fact, about both of these proofs that for holonomic approximation, this theorem for which you needed a positive codimension, that there you needed room to wiggle. Well, on a closed manifold, we don't have room to wiggle, so instead we just wiggle the manifold onto itself. And this is then the result of holonomic approximation. Okay, now, that was our first main result. And in the remainder, I want to apply this to Havliger structures. Because, well, recall we're actually interested in H principles, and there the central question was, if I have a formal solution, can I deform it to an actual solution? Well, Laudenbach and Meunier, they suggested to split this up into two steps. So you first try to homotope your formal solution into a singular solution, and then you try to resolve the singularities. And the second step is yeah, it follows again by Grommel's work on open manifolds, so that's doable. But for closed manifolds, it really depends on the relation. So I'll not focus on that. Instead, we'll look at the first step. Laudenbach and Meunier's proved that this could be done for contact in symplectic structures. And our goal is now again to show that it can be done for open and diff invariant relations. Now we just need to know what kind of singular solutions we allow for, and those will be formalized using Havliger structures. So for that, we need some geometry. And it's maybe good to say that a Havliger structure in literature is used for a lot of things, which then in the end turn out to be equivalent. For now, I'll just say that the Havliger structure is a foliated microbundle, but it will turn out to be equivalent to other definitions. So a foliated microbundle consists, first of all, of a microbundle, meaning that it is an equivalence class of germs of a fiber bundle around some zero section. And in fact, usually we identify M with its image under this zero section. And then because it's a foliated microbundle, we have a foliation on the fiber bundle around this zero section, meaning that, well, we have something that looks like this picture, but the foliation is locally just something which looks like Rn, and then all these sheets of a lower Rk. And then it's maybe good to say that if you have a foliation on your manifold, then you can pull it back using the exponential map to a foliated microbundle. And vice versa, if you have a foliated microbundle, you can restrict it to the base, and then you obtain a foliation. However, this only works if your manifold is transverse to the foliation, meaning that, yeah, the space, the manifold, and the foliation span is maximal. So in that sense, you could say that a foliated microbundle is a singular foliation, because, well, you don't really see it in this picture because my base manifold is one-dimensional, but would it have been two-dimensional and would I have drawn paraboloids, then you would see that the leaves intersecting the base manifold are one-dimensional, except where the foliation is parallel to the manifold, there it has a leaf of dimension 0, which is not allowed because we want our leaves to all have the same dimension. So this is one way in which you could think of a foliated microbundle as a singular foliation. Another thing you could observe is that if you have a foliation, you can only pull it back using a map that is transverse to the foliation. because otherwise you end up with a foliated microbundle. So foliations are not closed on their pullback, whereas foliated microbundles are, meaning that they just behave better. Now, why would one be interested in foliated microbundles? And this is really where they get the name Heffliger structures from, because we now see two of Heffliger's results on these objects. The first one states that foliated microbundles are in one-to-one correspondence with principal groupoid bundles, or actually isomorphisms classes of. And the groupoid we should work with is gamma, also called the Heffliger groupoid, and it consists of germs of local diffeomorphisms of Rn. So you could think of that these germs allow us to glue together the local trivializations of the fiber bundle. Now for the second result, we need to know what a concordance is, which you could think of as a cobordism of geometric structures. So we say that two structures, S0 and S1, are concordant if there exists a structure of the same kind on M times N, such that it restricts appropriately. Where structure could be here a foliated microbundle, but also a principal groupoid bundle. It's really a general definition. And with that, Heffliger proved that similar as for groups, there exists a classifying space for topological groupoids, meaning that concordance classes of principal groupoid bundles correspond in a one-to-one manner with homotopy classes of maps to the classifying space of G. And in particular, these theorems together imply that there exists a classifying space for foliated microbundles, really meaning that they're like topological or functorially well-behaved objects. Okay. Then going back to our original goal of studying H principles, we can now implement singular solutions as R microbundles. So definition will be on the next slide, but we implement them using these Heffliger structures. And in fact, it turns out to be useful to also introduce a singular version of formal solutions. So we refer to those as formal R microbundles. Now, what are these? Yes, that's a good note to make. Because we're going through our microbundles, that means we're not really studying H principles up to homotopy anymore. Instead, we'll be studying formal solutions and solutions up to concordance. So sometimes these types of H principles are also called C principles. But yeah, we usually refer to them as H principles because for foliations and foliated microbundles, the natural notion of homotopy is concordance because of this classifying space statement. Now, what are these R microbundles? Well, they consist of a foliated microbundle with some solution. So morally, you should think of it as having a solution on its leaf space. So I've drawn this foliated microbundle again, and then to the bottom of it, it's leaf space, and then on that space, we have a solution of the relation. And then we see that if the foliation on the foliated microbundle is transverse to the underlying manifold, the manifold actually embeds into the leaf space, and then the solution on the leaf space also defines a solution on M, meaning that an R microbundle can really be interpreted as a singular solution. However, this is just a moral definition. You cannot really work with this because, well, the leaf space is generally not a manifold, so it's hard to make sense of solutions there. So the official definition would be that we require a family of solutions of R on the fibers of E, invariant under holonomy, where this last part just means that if you're on a leaf and you walk along it, that the solution doesn't change, meaning that you get exactly what you want, which is a solution on the leaf space.
Quick question.
Yes.
R is a differential relation on base manifold or
No, that's a good point to make. So R is a relation on the fibers.
fiber
So
E or
yeah, of E. So this moral definition only makes sense if the dimension of the fibers and the base manifold agree, but in general, they don't need to. And then you could think of it as a family of solutions parameterized by the base manifold.
I see. So could you say that again what it means to have a solution in the leaf space?
Well, that was only a moral definition because that leaf space is a singular space. So around the singularities, it's hard to define. But if the dimension of the fibers and the base agree, then R, you could say, lives also on these singular spaces. And then an R microbundle consists of this foliated microbundle and a solution on the leaf space.
Uh-huh.
And then you can make sense of this using the different variants of the relation.
Okay.
Yeah. Well, maybe formally is not the right word, but officially you should think of it as a family of solutions.
Mhm.
Yeah? Okay. Then keeping in mind this official definition that we can use to define the formal analog. And then we again have, so we don't need a foliation in this case. So we really have less data here. So we just require a family of solutions, which are formal in this case, on the fibers of E. And we just need it along M. And then, yeah, one way which you could see that these formal R microbundles are like singular formal solutions is using this slide, because every solution defines an R microbundle and every formal solution defines a formal R microbundle. Similar to how every foliation defines a foliated microbundle using the exponential map. So we can use the exponential map to pull back the solution on the base manifold to the fiber. But this is what you were referring to. This only works, well, with this construction, we get the special case that the dimension of the fibers agree with the dimension of the base manifold. But in general, this does not need to be the case. And we'll actually see this in a minute. Then, result. So I've stated the result, but you can also look at the diagram, which I copied from earlier, because this theorem just states that the first step can be done for open and different variant relations. Meaning that if you have a formal solution, we just saw that defines a formal R microbundle, and this formal R microbundle can be concorded to a genuine R microbundle. Now, I want to claim that this is really an application of this holonomic approximation theorem into a tile space. So for that, I've included the proof. It is, however, one of these tautological proofs, which may not make sense the first time you see it, but just to indicate that it's a consequence of the previous theorem, I've included it here. And then there's also a picture written afterwards, which may help. But for the proof, there are two observations to make. So remember, we had this germ space consisting of germs of sections. Well, it has a subspace consisting of germs of solutions, which I denote by Etzel. And now comes the tautological part. Etzel consists of germs of solutions. So it has a tautological solution itself, using the different variants of the relation, because in each point, we define the solution to be the solution we're taking the germ of. Takeaway, there is a tautological solution on Etzel, meaning that there is also a tautological R microbundle. Now, the second observation is that by this earlier main result, we can find a map into Etzel, or generally into germ space, such that if we project it down to jet space, that map is homotopic to the formal solution we're given. And in fact, this map G into germ space lands in Etzel because it's an open relation. And now we can pull back the tautological R microbundle using G, and that's the requested R microbundle. So yeah, this theorem is really an application of the main result. Maybe this proof helps. So on the left, I've drawn the image of G in Etzel. So it consists of these sheets with singularities. And by these blue-greenish slices, I've tried to indicate the foliated microbundle, which is regular on Etzel because it comes from a solution. And then we pull it back to the base manifold, and then we get what is depicted on the right. So there we see a foliated microbundles with so-called wrinkle singularities of the foliation with the base manifold. Okay, now, second result states that this diagonal map is also possible, but here we see that the dimensions of the fiber and base become important. So what does this theorem tell us? Well, if we have a formal microbundle, which now does not need to come from a formal solution, then we can concord it to a genuine R microbundle, but only if the dimension of the base manifold is less or equal than the dimension of the fiber. And basically the proof is thicken the base manifold M such that it is of the same dimension, and then you're in the previous case and you can apply an analogous proof. But there is a more elegant way of phrasing this theorem, which is what I want to end with. So recall that we had this result by Heffliger that there was a one-to-one correspondence between foliated microbundles and principal groupoid bundles, or actually isomorphism classes of. Well, a similar result holds true for our microbundles if we upgrade our groupoid. So previously we used gamma, which was germs of diffeomorphisms of Rn. And now we also attach solutions, so to say. So we're considering this action groupoid because gamma acts on Etzel because it's a diff invariant relation. So morally, you could think of gamma R as all solutions of the relation and their symmetries. And these symmetries are encoded by gamma itself. And then we get this lemma. Well, to hopefully no surprise, there also exists a formal analog. There's just this technical detail that we get a concordance on the left-hand side. Sorry. And instead of germs of solutions, sorry, I had a bit of a cold last week, so my voice is not completely back up to speed. But okay, the formal analog. So this groupoid is now the jet analog of the groupoid we had on the previous slide. So we have jets of gamma, so jets of diffeomorphisms of Rn, and we have jets of solutions. But other than that, it's really similar to what we had before. Let's see. Oh, there it is. And because this formal groupoid, or well, it is a groupoid, but it's the formal analog of gamma R, consists just of jets of the objects in gamma R. There exists a natural map, which is just taking the jet. Um, and this then induces also a natural map between their classifying spaces because they're topological groupoids. So by this theorem of Heffliger, there exists a classifying space for them. And then, yeah, R is again an open and, or at least a diff invariant relation, and it lives on n manifold. So in terms of microbundles, that was our dimension of the fiber. And then this map has classically been studied for some relations by Havliker. Sorry. And then later also by Macduff, who proved that if you're considering the symplectic or contact relation, that this map is at least n+1 connected. And well, Sam showed that if you're considering the contact relation, that this map is at least n+2 connected. And we now consider the more general case of open and diff invariant relations. And then it turns out to be that this map is n-connected, or at least n-connected. And this is really a rephrasing of this result that was a couple of slides back about this diagonal map stating that formal R microbundles are concordant to a genuine R microbundle as long as the dimension of the base manifold M is less or equal than the dimension of the fiber. That's how we get the n-connectedness. And in fact, this theorem is weaker than the theorems above, at least in the symplectic and contact case. But we expect that for general relations, this bound is actually sharp. And yeah, that was it. With that result, I want to end.
Thank you very much. Yeah, it seems that you got a lot of germs from solutions.
Yeah. Quite inconvenient to work with at times, but
Any questions? I have some maybe random questions.
yeah, go ahead.
Uh, Somehow to prove the connectivity of these maps, it was important to think about diffeomorphism groups and the fact that diffeomorphism group has some sort of fragmentation. I mean, it seems that up to n connectivity is very H principle type argument, and
Yeah.
improving above n, at least in other cases, it was important to think about diffeomorphism group. But here, when you have a general differential relation, can one make sense of going from gamma R? Do you have an automorphism version of gamma R? Is there a way to globalize gamma R into some sort of a group, not a groupoid?
Mm, well,
What was the space of objects for gamma R? I forget.
it's Edsel. So the germs of solutions. What you could do is this groupoid is Morita equivalent to taking the same groupoid, but now germs around 0.
Uh-huh.
That is in some sense smaller. And then, yeah, in the contact and symplectic relation, you have a local model, so then it's even better. So then it's Morita equivalent to local model with symmetries,
I
but
see.
that's really a special case.
But somehow the morphisms are really from gamma n.
Yeah,
They're just local diffeomorphisms of Rn.
yeah,
I see.
yeah. Obtaining a group from this, yeah, I could only see this model where you take germs of diffeomorphisms of Rn preserving zero.
What would happen if you consider, say, the homotopy quotient of the action of def of Rn on the Etzel Rn?
Oh, yeah, I think if you don't have a local model, it's quite a horrible space because then you get all solutions, which there could be many.
Because gamma n somehow homologically is the same as def of Rn.
Yeah.
Um, and I thought that this is similar to the taking homotopy quotient, or maybe the groupoid action of def of Rn on Etzel.
Yeah. Yeah, I would have to think about what kind of quotient you get. But my intuition is not that it's a particularly nice or easy space.
I see.